Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. Let's derive the rule on differentiating a power. This next rule is somehow known as the rule for the differentiation of a power or an exponentiation, which states that if n is any number and if f of x is equal to x to the power of n, then the first derivative is equal to n, the exponent, times x to the power of n minus 1. We are to show here the proof using the definition of differentiation or a derivative. Now, take note, our f of x here is x to the power of n in this form, okay, where n is the exponent and x is our base. Then the definition of the derivative of that is equal to the limit of f of x plus the increment of x minus f of x over the set increment of x as the increment of x approaches to 0. We are going to use this as we signify later on or generalize this rule, which will be used later on some examples. Other books uses this, by the way. Let me just simply show this to you. Instead of the increment of x, they use h for easier derivation and use in examples, but of course they are just the same as the increment of x is just h. But let me use this definition as this indicates smaller changes in x, hence delta x or increment of x. Now, we are going to show that from here, we will reach this form, n times x to the power of n minus 1. This is what is being used for solving derivative of polynomial functions or functions just like this. But of course, we need to show its truth value here. I may be using a lot of spaces, so please bear with me. So here is the proof. Okay, as we will have f of x. Okay? Take note that this is our function. We will have here the limit per definition f of x plus increment of x or delta x minus f of x over delta x as delta x approaches to our 0. In a separate piece of paper, we are going to use here what is f of x plus increment of x. Take note that our definition is x to the power of n. So this is actually this value, x plus increment of x to the power of n. Okay, this be guided. And of course, f of x, this value here or expression is what is given as x to the power of n. We are going to substitute that here and here and simplify it further and solve for the limit if it would return to this form. So let's do it step by step. You will have here the limit of this first, this one here. You will have here x plus delta x or increment of x to the power of n minus x to the power of n over the increment of x. Of course, you cannot cancel this and that. Okay, don't do that because this is under an exponentiation. Hence, to generalize that, we are going to use here the binomial expansion or the binomial theorem. So before we continue with this, let's of course give the representative expression for this using the binomial theorem. And if you can still remember, the binomial theorem or binomial expansion using this will have to share this exponent to the first and second terms by the decreasing order for the first term but increasing order for the second term, and a combination of the selection of n. Let me use this. Okay, I don't know if you can still remember this, but I'm going to show you this form immediately because our goal is to show the proof for the rule of differentiating a power. You will have this form here, okay, n taken 0, okay, times x to the power of n. The first exponent has n while this has 0. And this is a binomial expansion, okay? Plus, you have here n taken 1, then x n minus 1, and then your second term, increment of x will have 1 now. So as you can see, the exponent of x is decreasing, but for delta x or increment of x is increasing. You also have another plus n taken 2, x to the power of n minus 2, you have delta x squared, okay? Plus dot 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 until let us have the second to the last term. We have here n over n minus 1. Okay, before we reach n, because that's the final part, you have here x, you have here delta, that's x to the power of 1, delta x, you will have n minus 1, plus you will reach your last value here of n, taken n, sorry, this should not be fraction because this is under combination, n taken n, x to the power of 0, delta x to the power of n. Okay, or you could simplify this further. You could have removing the 0 exponent. Okay, so just like this and that, or let me just automatically remove this. Hopefully you're able to understand the trend of the exponents. Again, for delta x 0, 1 until you reach n, but for your x is n minus 1 until you reach 0. Okay, so let me remove some scribbles here, and of course this will become 1, okay? And this will also become 1. This is the form of just this idea here. So going back to that, you will have here the limit of that form. So you will have here n, by the way, n taken 0 in combination is just equal to 1. Okay, sige, let me have here, but n taken 0, no, sorry, n taken 0, n taken 0 and is equal to n taken n, sorry, I am used in writing rational expression, which is equal to 1. So this could be just removed, and this will also be removed. Hence, again, let me rewrite this. So we have here the limit. Writing all of this, you have x to the power of n plus n taken 1, x to the power of n minus 1, then delta x, because that's the power of 1 here, plus n taken 2, x to the power of n minus 2, the square of delta x, plus dot, plus this, n over n minus 1, x, delta x, n minus 1, and plus, since this is 1, delta x raised to n. This is just this idea here, this one here. Take note, we still have this form, minus x to the power of n. Okay, take note of that, minus x to the power of n, all over delta x, as delta x approaches to 0. Other references would like to use h because it will not complicate the proof, but this is the proof using delta x. Now, I'm combining them. Again, this entire form here is just this. Okay? Using the binomial theorem, we had that difficulty because the exponent is n. Take note of this one here. I would like you to look into that in this final form here. X to the power of n minus x to the power of n, so that's equal to 0, right? They will be equal to 0. And look into all the remaining terms of our numerator. We have, let me change the color to red, delta x, delta x, delta x, delta x. Okay? So we can factor delta x. Why? Because we have a delta x in our denominator, and we can cancel that, and making sure that this is no longer equal to 0 as we substitute the delta x approaching to 0. Okay? So what's the next step here? This should be the limit. Since this is already removed, you factor delta x on your all the terms in your numerator. So you will have here, okay, still n taken 1, but x to the power of n minus 1 now. Okay? Plus, you will have here this, n taken 2, x to the power of n minus, sorry, this is n minus 2 if I'm correct, right? Let me return, yeah, n minus 2, sorry. n minus 2, once you take out 1 delta x, you still have delta x here. You still have delta x here. So n minus 2 times delta x plus dot plus n over, not so, oh my god, again, I am sorry, I am used to writing rational expressions. N taken n minus 1, x, as you take out here delta x, you will have delta x n minus 2 because that's minus 1. And then plus, as you take delta x here, you will subtract it by 1. All over, this is all over delta x, as delta x approaches 0. Now, as mentioned, you can simply cancel that, and instead of having a rational expression, you will have a polynomial expression in this form, which is easier to substitute delta x approaching to 0. So you have here n taken 1, x to the power of n minus 1. Okay? Then you will have here plus n taken 2, x to the power of n minus 2 delta x, plus plus n taken n minus 1, x delta x raised to n minus 2 plus delta x raised to the power of n minus 1 as delta x approaches to 0. Since there's no more delta x in the denominator, we can simply substitute this one. So this would become 0, hence this entire expression is 0 because this is 0, right? Other forms here will also have delta x's, so everything here will also be 0. This is 0, hence this is 0. This is also 0. Leaving us with the final form, the limit of n taken 1, x n minus 1 as delta x. Because we already applied the limit, so we'll have this form. We already substituted delta x approaches 0, so we have this. N taken 1 is actually n in combination. N taken 1 is n. As earlier, n taken 0 is 0, 1, sorry, and n taken, this one here, n taken n is 1, n taken 1 is n, times x to the power of n minus 1. And what is this? Finally, we have reached the conclusion we're trying to reach. From this portion, we have verified this. Therefore, using this proof, okay, is equal to n times, let me rewrite this again, equal n times x to the power of n minus 1. And this is actually the rule for differentiating a power, and we are using this, and we will be using this for future examples. But this is the proof of this rule or theorem for differentiating a power. Thank you very much for watching. So what are you waiting for? Subscribe now.